Good morning. My name is Dr. Ripon Patgiri. My co-author name is Dr. Molaya Dattabora. We are from National Institute of Technology, Silchar, India. We are going to present HEX-BLOOM, an efficient method for authenticity and integrity verification in privacy-preserving computing. Merkle tree is applied in diverse applications, blockchain, smart grid, IoT, etc. to verify authenticity and integrity. Recent developments suggest that Merkle tree is adapted in numerous applications. However, the Merkle tree is computationally costly data structure. It uses secure hash function to partially verify the data integrity and authenticity. Merkle tree allows verification of data blocks authenticity and integrity after successfully downloading a particular data block using Merkle root, for instance, peer-to-peer torrent network. Moreover, the time complexity of Merkle tree is high. In addition, Merkle tree requires high memory to store entire hash value. Each block requires a few hash value which require network access. Therefore, it degrades the performance of Merkle tree and increases the network threat. Merkle tree's performance depends not only on the time complexity of the data structure but also depends on the network latency and network traffic. Also, the verification of particular block is costly due to network access. The partial verification process of the Merkle tree is disadvantaged and it should be obviated. Also, the time complexity can be further reduced. The Merkle tree is M-array or M-way tree of order M, where Merkle tree is rooted tree. Each node can have at most M-1 keys. Each node can have at most m children and keys are not in sorted order. Merkle tree, let L be the number of blocks. These blocks are hashed using secure hash function and these hash values are used to build the Merkle tree. Therefore, there are L leaf nodes in the tree. An M-array Merkle tree has I internal node. It shows that it is an overhead of I hash functions. The total number of leaf nodes is n. Issues of Merkle tree. Let us assume that a set of block L consists of millions of blocks. Then it is not feasible for a conventional computer to construct the Merkle tree. Merkle tree construction requires big O n log n hash function calls, which is time consuming. As a result, it is not feasible for a large set of blocks. Merkle tree cannot be constructed by B3, B plus 3, any other search tree. Merkle tree uses secure hash function to construct the tree. Merkle tree requires extra space of big O n and it is costly due to large size memory requirement per node. Merkle tree creates massive network traffic. Bloom filter is a probabilistic data structure. It is used for approximation membership filter. It can answer either yes or no. Yes or no answer can be true positive, false positive, and true negative. The time complexity of insertion, query, and deletion in Bloom filter is big O k, which is equivalent to big O 1, where k is the total number of hash function. The extra space complexity of Bloom filter is mu bits. This is the comparison table between Merkle tree and Bloom filter. Linked hash X. We propose a new variant of Merkle tree using hash and XOR operation, linked hash X for short, which is used to replace Merkle tree. Linked hash X maintains its root. Unlike Merkle tree, it doesn't maintain entire data structure. Linked hash X uses secure hash function. So it is elaboration of the equation 1. Linked hash X publishes two roots, H root and H dash root publicly, and it keeps HR and HR dash as a private. So comparison between Merkle tree and linked hash X. Merkle tree building cost is big O n, where linked hash X cost is big O L. Verification of a block is a big O log n, where linked hash X doesn't support verification of a block or partial verification of a block. Verification of all blocks in Merkle tree takes big O n log n, where linked hash X takes big O L. Extra space complexity of Merkle tree is big O n, where linked hash X takes big O 1. So HEX-BLOOM is a combination of Bloom filter and linked hash X. Merkle tree is costly in terms of time and space complexity and networks, as we have already discussed. Our proposed system combines both linked hash X and Bloom filter. In the construction process, it requires to construct linked HEX as well as Bloom filter. All hash values are inserted into the Bloom filter. Similarly, the construction of linked HEX requires big O of L cryptographic hash function and big O of L JOR operations. Bloom filter requires big O of L insertion operation with big O of K into L non-secure hash function. Non-secure hash function is much faster than secure variant. The Bloom filter and the root of linked HEX are maintained for future use. The verification process requires the linked HEX root and Bloom filter, which are downloaded from the trusted node or server. Linked HEX node root contains the JOR value of the last hash value and the hash value of final results, that is H root and H dash. Extra space is Merkle tree takes big O of n, where our solution takes mu bits only. Verification of a block is Merkle tree takes big O of log n, our solution big O of k. Verification of all blocks, Merkle tree takes big O of n log n, our solution takes big O of k l. A network access for a single occasion. The partial verification process requires Bloom filter because linked HEX doesn't support the partial verification. A block is verified in Bloom filter for its authenticity after completely downloading the block, and at the same time the user can construct the linked HEX root. Thus, the Bloom filter gives approximate verification of a block's authenticity and integrity. Linked HEX is constructed by the user while downloading the data. When all processes are completed, the constructed linked HEX root is compared with the downloaded linked HEX root. So this is the comparison between Merkle tree. Our solution takes big O of KL, where is less than big O of N, big O of L, where our solution takes big O of 1. So Merkle tree is deterministic. Our solution is probabilistic and deterministic. So in this paper, we unearthed the drawback of the Merkle tree and propose a new solution that is called HEX-BLOOM. HEX-BLOOM is significantly faster than state-of-the-art Merkle tree, which is presented using big O of notation. Moreover, it consumes less memory than the state-of-the-art Merkle tree. We have demonstrated that the Merkle tree creates unnecessary network traffic, which is addressed in our proposed system. State-of-the-art Merkle tree requires network access to verify a block, and therefore it is time-consuming, and its performance depends on the network latency. Overall, HEX-BLOOM outperforms the state-of-the-art Merkle tree in every aspect. Thank you.